About 17,000 years ago, an ice sheet covered much of the landmass of northern Britain and also spread into the Irish Sea basin. One of the last pulses of this ice terminated on the Cumbrian coast, piling up huge heaps of glacial moraine, sand, gravel, clay, and masses of ice embedded in these sediments. These chunks of buried ice could be of substantial size, meters or tens of meters across. In time, this ice would melt and the ground subside, leaving hollows called kettle holes. This is what a kettle hole looks like soon after its formation. When water fills the hole, it will provide a record of sedimentation for thousands of years. This landscape along the coast just south of St. Bees is full of remnant kettle holes, some containing ponds and still accumulating sediment up to the present day. Others have been completely filled with sediments, though their locations and earlier contributions to the landscape are obvious. Along the cliffs, such a filled-in kettle hole is exposed in cross-section, providing easy access to nearly 5 meters of sediment. These offered the chance to study climatic change in a datable succession from the basal sediment, around 13,000 years old. These changes have been marked out using coloured tape. Red, indicating a relatively warm period, blue, a very cold period, and white, a cool climate. Sometimes, but not always, the colour changes correspond to changes in sediment type, ranging from light brown sandy material to dark brown fibrous material, or peat. The peat and sand layers record a succession of quite rapid climate changes over a span of 2,000 to 3,000 years following the retreat of the ice. The sequence of events was worked out by Russell Coop.
What you can see from this section is that the change over from inorganic to organic and then back to inorganic again above is very, very quick, and may well have tended to suggest that we were dealing with very rapid climatic changes. In the late 60s, I came here looking for the evidence of climatic change based on fossil beetles. And this material that is here, this peaty stuff here, is absolutely jam-packed with insect remains, of which beetles are one of the most abundant.
The sediments in this layer are very similar to those forming in small lochans in Scotland today. The bottom is a litter of organic material destined to become the basis of peat. Water plants thrive. This one's bog bean, named after its characteristic seeds.
Right.
Right.
Now, what's here? Can you just... Oh, yes, look. 2 little seeds there. That's certainly bog bean. It's obviously been a marshy pool.
Look at these here.
That's bright green.
That's a piece of Dytiscus. That's one of the very, very large water beetles.
210 species of beetle have been found in the St. Bees section. By comparing the fossil populations with those found today, either in the water or blown onto it from nearby plants, deductions can be made about paleoclimates.
Down here, we had only temperate beetles. This was quite surprising because we thought down here we would get Arctic species. Because only just below us, somewhere down here, there are the glacial deposits which you see in the cliff. If I look at this bit here, one of the commonest beetles in that lives no further north than Kent at the present time. And yet it was up here, and in such numbers as it must have been breeding here. They're not just accidental fly-ins. So this is clearly very warm, and this is warm too. And down about here, I've got a beetle that only lives no nearer than Provence.
Gracious.
And that's a little carnivore. And so is this a little carnivore, by the way. But this means, therefore, that it's eating things like springtails and collembola and things like that.
So it doesn't need trees, but it does need a very warm temperature.
It needs a very warm temperature. You must remember that this sort of stuff was Arctic, far, far too cold for trees to grow. And suddenly, the climate changed. But the trees weren't here. The trees were in the south of France or Italy or
Yes.
somewhere way down there. If they'd set out from Italy, it would take them quite a long time to reach here.
Yes, particularly something like oaks, where you've got an acorn, doesn't travel very fast.
But don't forget the beetles are very, very mobile. Not only are they very mobile, but they go through one generation per year, so that they can reproduce very, very rapidly and spread into new areas. Now, the beetles tell another story. When you get to here, at this point, all my temperate species start dying out, and they've completely died out by there, and are replaced by North British, sort of cool temperate things, suggesting temperatures somewhat cooler than present time, but not a lot cooler.
And this is when the birch actually begins
Yeah.
to spread.
Yeah.
So the birch was really more the sort of conditions that we find birch growing on in Scotland. or-
Exactly. It cooled down and humus started to accumulate in the soil. And this meant that soil retained moisture. And this moisture meant that you could grow trees more easily. And so for a period here, we have total harmony between the beetles, the plants, and the sediment, and the whole ecosystem seems to make sense. Here, there seems to be disharmony as the pioneers fight for opportunities and spread in gradually colonizing, each at their own particular rate. And we have therefore a climatic deterioration here of some 4 or 5 degrees. And it looks as if it happened then,
And that is...
a step. And
And your southern warm temperate beetles go out pretty suddenly. And
they
all-
go out, every one of them. And what go out are not just particular ecological types, but carnivores, phytophags, water beetles, terrestrial beetles, which suggests that it's a pretty fierce climatic event. Now, as you go up to here, and the next time gap is somewhere in here, there's a big lithological break there. And here, the cool, temperate beetles are now accompanied by northerners. And by northerners, I mean high Arctic, high altitude beetles, some of which live no nearer than the Kanin Peninsula in Arctic Russia. From there upwards, all where this blue tape is going. Charles, if I can borrow your hoe for a minute, I can use it as a pointer up there at the top of the cliff. Hold on a minute. Right. Most important is just there, we got enough terrestrial material to get a radiocarbon date. And up there, it was 10,500 years ago. And if you come right the way down to here, 11,500 years ago. And then if we went right down to the bottom, 12,500 years ago. So see the different rates of sedimentary accumulation. 1,000 years here, and 1,000 years from here, right the way up to there. Now, for convenience, again, those little tapes have been put in to show where again there's a sudden climatic change, for above that is post-glacial material, from there upwards. And that post-glacial is temperate. And although not from this site, but from other sites, we've got insects and plants from there, immediately you get the incoming of birch up there again, with a whole suite of temperate insects. And again, this is a very, very sudden change.
"15 miles to the west of St. Bees, the Lake District reflects the topographical expression of repeated glaciations during the cold stages of the Quaternary. The Wastwater Screes. Frost shattering continues the erosion of several glaciations. Approaching Styhead, a high mountain pass cut and smoothed by the moving ice. Mickledon, a valley once occupied by a small glacier. Hummocky Moraine, which we still find today, is evidence of the final retreat of the glacier from this valley. In this final cold period in the Lake District, ice had reoccupied corries. These are armchair-shaped hollows excavated by previous glaciations and usually quite high in the mountainside. They would have contained very restricted cirque glaciers, like this one on Mount Edith Cavell in Canada. Today in the Lake District, the corries are often occupied by a corrie lake or tarn. Their size is apparent by a wall of terminal moraine, forming an arc-shaped dam on the valley side of the corrie. Although this amount is exceptional and might include material from older glaciers. Reconstructing the glacier here at Bowscale Tarn, you have to imagine that the ice went up to the top of the back wall and filled the bowl, which now has a small lake in it, which is up to 16 meters deep. The glacier would have sloped gently down to the large dump of moraine, beyond which is an outwash slope, where meltwater would have flowed into the valley below. John Boardman has worked extensively on glacial events in the Lake District.
What we really want to know now is something more about how precise we can be about the timing of these events. Can you tell us something about that?
We can't be very precise, but we can say certain things about the timing of these events. We can say that these glacial events were the last glacial events to affect the Lake District. We can look at the freshness of the forms and observe that they've not been much affected by geomorphological processes since the glaciers were here. So that's one point. The second point is that there is a little sedimentological evidence from corrie lakes like this one at Bowscale, which shows that these basins were full of ice during the Loch Lomond Stadial, and the ice melted towards the end of that event. So perhaps between 10,500 and 10,000 years ago they became free of ice, and that's true here.
So this cold event that generated these corrie glaciers is approximately equivalent to what we've seen on the Zimbabwe coast, where we have that inorganic sedimentation that seemed to have been deposited under Arctic conditions down there, was reflected up here in corrie glaciations.
Yes, a rather minor glacial event of restricted extent, which saw about 60 corries in the Lake District occupied by small corrie glaciers, and one or two of the major valleys in the central Lake District occupied by short valley glaciers.
This stage, which is known either as the Younger Dryas or the Loch Lomond Stadial, is marked in Scotland by a much more extensive glaciation, stretching as far south as Loch Lomond.
I'm sitting on the outermost moraine of a glacier in Glen Torridon in the Northern Highland of Scotland. And as you can see, it almost reached present-day sea level. From this point here, if I'd been around 10,500 years ago, I could have walked all the way south to the south end of Loch Lomond without leaving the great ice field that formed in the Western Highlands of Scotland at that time, a distance of perhaps 200 kilometres. This ridge is part of an extensive chain of glacial moraines that rings some of the highest mountain areas in Scotland. Collectively, these moraines define the limits of a very large ice field, about 5,000 square kilometres in extent, that existed here about 10,500 years ago.
Here is a contemporary example of a lateral moraine defining the limits of a glacier in Canada. But how can we determine where the ice has come from?
Most of these boulders on the side of the ridge are just the local schist. It's this rounded one we're interested in, isn't it?
That's right. This, as you can see, is a granite. And so it's totally foreign to this area. The underlying rock is entirely schist.
So where's this come from?
Well, this is a distinctive granite that's come from Rannoch Moor, from the Rannoch Moor Basin.
Over there?
That's right. Something of the order of about 20 kilometres it's been carried to reach this side here. And of course this gives us very solid evidence of where the glacier that deposited it has come from.
Right.
This must have passed from Rannoch Moor through the intervening ring of mountains and being dumped on the terrain here.
Rannoch Moor is the basin in which the build-up of the Loch Lomond icefield was centred. The thickness of the ice here finally reached about 300 metres. We know that because trim lines defining the boundary between ice-smoothed rock below and frost-shattered rock above make it possible to estimate the altitude of the ice surface. Scotland, 11,000 years ago maybe? How long would it take for such a large ice mass to build up?
At the moment, such estimates as we have suggest that the sort of climatic pattern for an ice mass of this size indicates that precipitation in this area was perhaps very slightly less than it is at present, but that mean annual temperatures had dropped perhaps about 6 degrees centigrade. Then we'd have expected build-up of ice within a few centuries to the sort of dimensions that we've mapped in this area. Near to Glen Torridon in the Northern Highlands of Scotland is Corriachudnock, the Valley of 100 Hills, an area of apparently randomly scattered mounds and hummocks of glacial debris. For some years, this area of apparently chaotic topography was interpreted as an area of glacial down wastage. It was thought that after the last glaciers reached their maximum extent, the ice down wasted in situ, with debris falling into crevasses and being piled up as a series of apparently random mounds and hummocks. More recently, however, geomorphologists have given more attention to studying the pattern of these features and their internal structure. And these have shown that far from being random in pattern, they describe a series of crescents that mark the retreat pattern of an active glacier, not one that merely decayed in situ.
These morainic ridges mark a succession of pauses as the ice front retreated towards the right. On Rannoch Moor, we can make out similar morainic ridges, which again mark the final stages of the ice front as it retreated at the very heart of what was once the last extensive ice field in Scotland.
Now, this pattern has major implications because it establishes that the glaciers of this period reached their maximum limit long before the climatic warming that terminated the Loch Lomond Stadial. And this has led us to revise our view of this climatic period into three separate parts. The first part, a period of cold, moist, snowy weather, which was conducive to the growth of glacier ice to its maximum limits. The second part, a period when the glaciers underwent an oscillatory but active retreat. And we believe that this was probably due not to a warming of the climate, but to a drying up of the climate. Glaciers ceased to be sustained by as much snow as previously. And following this period of active glacial retreat, it appears there was a very rapid warming, perhaps of as much as 1 degree centigrade per decade, and that terminated the cold period of the Loch Lomond Stadial and killed off any remaining glaciers.
Having seen some of the evidence, what about the mechanisms that underlie these climatic changes?
One of the interesting things that comes out of, if you like, geological studies is that the Gulf Stream can't be trusted to stay there for very long. And in fact, for long periods in the recent past, i.e. sort of 20,000 years ago, the Gulf Stream didn't flow up our west coast, but it in fact cut back somewhere here at the latitude of central Portugal. And that polar front has a position of, well, approximately there. South of this area, we had nice warm water, but to the north of it, a gyre, a sort of huge whirl of oceanic water up here, which was cold. It was cold sufficiently to bring pack ice right the way round on it and for the pack ice to get grounded up our west coast. Now, what is emerging from studies of the North Atlantic, from boreholes that have been drilled into the sediments, is that this situation is also impermanent, and that every now and again the configuration of these huge whirls of water here changed. So that by 13,000 years ago, it was approximately in that position there. Let's continue somewhere up here. It goes up the Norwegian coast, something like that.
So you had the Gulf Stream then actually coming up here, but then turning back, say, in
Yes.
this direction.
Exactly. And this will have enormous climatic implications for the flora and fauna of Western Europe in general, and particularly for Britain and to a very large extent Ireland, because they're on the receiving end of the sudden change, the sudden switch from polar water with pack ice to warm temperate water. And the difference in summer temperatures of the water on either side of this polar front may have been as much as 7 degrees centigrade. It means that, in fact, when the pack ice was present on our west coast, it was too cold for trees to grow. And in theory, once the polar front has gone past, you could have grown oak trees. Whether it did or not is a different matter. Now, curiously enough, just as I said that the position of the Gulf Stream was itself impersistent, shortly afterwards, the northern gyre reasserted itself, the Gulf Stream withdrew. Let's draw it about there. So that you can see, even off the west coast of Ireland, there was a sudden return to Arctic conditions. When was that? Well, it was about 11,000 years ago. Now, in its turn, this then migrated back again to a position like this. So that by 9,500 years ago, let's put it 9.5.
You're virtually back to the present day.
You're back to the present day. There is a sort of flip-flop here. 14,000 years ago there, 13,000 years ago there, 11,000 years ago there, 9,000 years ago there. And each time this polar front flaps backwards and forwards along our west coast, it either introduces warm water or introduces polar water. Therefore, the climate on the west coast of Britain in particular, Western Europe in general, is going to dance to the tune of this varying flip-flop of movement between the polar water and temperate water.
Now, when you get the polar front moving southwards, how does this actually affect weather patterns here on the land?
If we have a southward movement of cold water in the North Atlantic, this is liable to create a zone of enhanced cyclonic weather, in other words, low pressure type weather, crossing the British Isles, particularly the northern part of the British Isles, under colder conditions than those of the present. In other words, ideal conditions for the build-up of glacier ice. However, if that line between the warm oceanic water and the cold oceanic water moves even further south, then it's likely that the most northern parts of Britain would start to experience a more arid climate. So it may be that the movement, the progressive southward movement of cold water in the Atlantic, is intimately related to the phases of glaciation that we've seen in the land surface in Scotland.
Let's put all of this into some kind of context. Major changes of the global climate during the Quaternary Ice Age have been related to cyclical changes of the Earth's orbit around the Sun. Such a change occurred with general warming and ice retreat from about 15,000 years ago onward. But the Loch Lomond Stadial was a very short but intense cold period on a quite different scale, interrupting this general warming. Its cause is still a puzzle. One theory looks at the consequences of melting the huge Laurentide ice sheet, which was still covering much of North America. With the ice sheet at its maximum extent, meltwater drainage from an enormous area will be concentrated to flow down the Mississippi Valley into the Gulf of Mexico. The map shows the Laurentide ice sheet at its maximum about 18,000 years ago. Between the Rocky Mountains on the west and the Appalachians on the east, meltwater drained south by rivers all feeding into the Mississippi. Then, as the ice front retreated north, it left proglacial lakes along its margin. And at 13,500 years ago, meltwater was still being drained into the Mississippi watershed, mainly from overflow from two of these lakes. When the ice retreated even further north, more proglacial lakes developed, and by about 11,000 years ago, the old exit through the St. Lawrence River and out into the Atlantic became unblocked. Some of the meltwater from the ice sheet was drained eastwards via this new spillway. When this happened, the North Atlantic Ocean would suddenly receive a great influx of cold meltwater, drastically reducing sea surface temperatures. So could this be the reason why the process of warming and ice retreat along its continental margin was temporarily reversed? But by 9,500 years ago, the polar front was pushed right back against the Greenland coastline, and there it's remained until the present day.
Well, the ice cores taken in the very centre of Greenland reflect the comings and goings of the Gulf Stream. And the ice core men have got a means of dating which we don't have. They can count down the layers of ice, summer ice, winter ice, and so on, and can therefore get a very precise idea of how long it takes to go from a cold to a warmer episode. And surprisingly enough, whereas we down here at St. Bees can say that these changes, for instance, from cold to warm, took place suddenly, i.e. in less than 100 years, the ice core investigators are now suggesting that the change may be over a period of a decade, or even less.
Ooh, that's really fast.
But we needn't worry us over much. We are probably not going to be subjected to the same frequency or intensity of climatic oscillations that characterized the end of the last ice age.
So the interglacial mode, which we're in at present, is really rather more stable than the glacial mode.
I think so. At least I say so optimistically, because there are people now who claim that even within the last interglacial, there were oscillations which reintroduced polar conditions. Short ones, but nonetheless
It's a bit controversial still.
It is controversial, but it's a hint that perhaps this stability, which we fondly imagine characterizes interglacials, may not be entirely well founded. It may just be optimism, and optimism is a very dangerous precedent for establishing scientific truth.